Hey everyone, and welcome. Today, we're diving into something that starts with a super simple summer treat, but believe me, it ends up with some seriously cool physics. It all kicks off with a question you've probably never even thought to ask. Yeah, you heard that right. Could that cup of shaved ice you get on a hot day secretly be a legit workout for your body? I know, it sounds a little bit absurd, but the answer is actually locked away in the science of heat. So, to figure this out, we gotta dive into the science. So to figure out if this is a real workout, we first need to get a handle on the basics of how heat, which is just energy really, actually moves from one place to another. Think of this next part as us building a little physics toolkit. We're just going to grab the essential concepts we need to solve this whole snow cone mystery. And first up on our list are the three main ways heat gets around. So, the first part of our toolkit covers the three classic ways heat moves: conduction, convection, and radiation. And trust me, you experience these things every single day, probably without even realizing it.
Okay, so first, we've got conduction. This is just heat moving through direct touch. Imagine you're cooking and you leave a metal spoon in a hot pot of soup. You come back, you grab the handle, and ouch, it's hot. That's conduction. The heat energy literally traveled right up the solid material of the spoon to your hand.
Next up is convection. Now this is heat transfer through flow, through movement. The classic example is a space heater in a room. It warms up the air right next to it, right? Well, that hot air gets less dense and rises. As it rises, it pushes the cooler, denser air down towards the heater to get warmed up. And you get this constant circular flow, a convection cell, that eventually heats up the whole room. And number 3 is radiation. This is heat that travels as a wave, kind of like light. You can feel the warmth from a campfire from all the way across the campsite, right? You're not touching it, and you're not in the path of the rising hot air. That warmth you feel on your face, that's infrared radiation traveling through the air and hitting you. So, to boil it down, conduction is heat by touch, convection is heat by flow, and radiation is heat by waves. Got it? Okay, so that's the first part of our toolkit. Now we just need one more piece to this puzzle. Now, this is where it gets really interesting. See, adding heat doesn't always mean the temperature changes. To really understand our snow cone problem, we have to get the difference between two really important ideas: specific heat and latent heat. Specific heat is what we usually think about. It's the energy you have to add to actually make something hotter. When you put a pot of water on the stove for pasta, you're adding energy, measured in joules, to raise its temperature, degree by degree. And for water, that number is pretty specific: 4,186 joules for every kilogram of water you want to raise by 1 degree Celsius. Okay, but that leads us to a classic physics riddle. Think about a block of ice melting. The whole time it's turning from solid to liquid, its temperature is stuck at exactly 0 degrees Celsius. So if you're constantly adding heat to it, but the thermometer isn't going up, where is all that energy actually going?
And the answer is latent heat. It's kind of like hidden energy. That energy isn't raising the temperature at all. Instead, it's being used for a completely different job. It's breaking apart the molecular bonds that hold the water molecules together in that rigid, icy crystal structure. It's the energy it costs to change its state. And this table just lays it out perfectly. Specific heat, which we call C, changes the temperature. Latent heat, or L, changes the phase or state: solid to liquid, liquid to gas. They both require energy, but that energy does two totally different things.
All right, our toolkit is officially complete. We've got conduction, convection, radiation, and now we know the difference between specific and latent heat. We are finally ready to go back to our snow cone and figure out the energy cost. Let's do the math. So, when you eat a snow cone, your body has to do two big things. First, it has to supply enough energy to melt all that ice, which is sitting at 0 degrees. That's a phase change, so we're going to use latent heat for that. Then second, it has to take that freshly melted water, which is still at 0 degrees, and warm it all the way up to your body temperature, which is about 37 degrees Celsius. And that's a temperature change, so we'll use specific heat. Okay, step 1. Melting the ice. A typical snow cone is about 237 grams. While the latent heat of fusion for water is a whopping 333,000 joules for every kilogram. You run the numbers, and it turns out your body has to spend nearly 79,000 joules of energy just to turn that solid ice into liquid water. Now for step 2, warming up that cold water. We have to raise the temperature of that 237 grams of water from 0 all the way up to 37 degrees. Using water-specific heat,
That calculation comes out to just over 36,500 joules.
And now we just add them together. The energy to melt the ice plus the energy to warm the water gives us our grand total. Your body has to burn over 115,000 joules of its own energy just to process a single snow cone. But what does that number actually mean? Is that a lot?
Well, to put it into perspective, we need something to compare it to. So let's use an actual exercise. The source material we're looking at estimates that doing one single push-up requires about 400 joules of energy. Okay, now we have everything we need for the big reveal.
And there you have it. You take the total energy your body burns on the snow cone and divide it by the energy for one push-up, and you get 288. That's right. Eating one snow cone forces your body to expend the same amount of energy as doing 288 push-ups. So, is it a workout? From a pure energy standpoint, you bet it is.
Now, this is more than just a fun party trick, right? These exact same principles of heat transfer are absolutely critical to how we design things for everyday life. Everything from the clothes we wear to the houses we live in. Let's just take a quick look at one example.
Ever wondered why an oven mitt actually works? It's all about slowing down conduction. The mitt is thick, which increases the distance the heat has to travel to get to your hand. It's made of a material with low thermal conductivity. It's a terrible conductor of heat on purpose. And you only grab a small part of the hot pan, which reduces the area for heat to transfer through. It's just simple physics in action.
You know, when you really boil it all down, everything we've talked about today comes back to this one simple, really powerful idea. Heat is just disordered energy. And it's always trying to spread out, to move from hot to cold, from a state of order to disorder. And our goal, whether we're eating a snow cone or wearing an oven mitt, is just to manage that flow.
So, we'll leave you with this final thought. Now that you get the core ideas of conduction, convection, and radiation, how can you start applying that to your own life? What choices could you make with your clothes or your home to manage that flow of heat better and keep yourself more comfortable all year round? Something to think about. Thanks for tuning in.